Welcome to session 7 of electronic structure theory. In this session, we'll be talking about two more of the methodologies that are commonly used to treat dynamical correlation and the dynamic dance that the electrons undergo in atoms and molecules. And these are called the configuration interaction, CI, or the multi-configurational self-consistent field, MCSCF methodologies. We'll be talking about these two things and comparing them to the thing we talked about in session 6, which was Møller-Plesset perturbation theory. And we'll be dealing with talking about how these things scale with the number of atomic orbitals in our basis function and how the computational difficulties scale with the number of what's called Slater determinants used in the configuration interaction or MCSCF expansion. So that's what we're going to be doing in session 7. Welcome to session 7 of electronic structure theory. Okay, so last time we talked about the Møller-Plesset way of going beyond the Hartree-Fock theory to put in electron correlation. Today, on this session, we'll talk about two other methods, what's called multi-configurational self-consistent field, MCSCF, and configuration interaction, CI. But first I have to tell a joke about MCSCF. I was in the chemistry department years ago, and I saw this seminar that said MCSCF CI study of some molecule. So I thought I should go to this seminar. But it was on a day that wasn't usually a physical chemistry seminar day, so I was suspicious. So I showed up to the seminar, and I sat in there, and the speaker put up his first slide that said multi-component supercritical fluid chemical ionization study of this compound. And it was an analytical chemistry seminar. So acronyms are not necessarily uniquely defined. But anyway, MCSCF, this multi-configurational self-consistent field. The idea here is that if you're in a situation where you know that a single Slater determinant is not going to be adequate for you, and this would be, for example, if you're doing that singlet S carbon atom where one determinant just can't do something that's singlet S, you need those three determinants. Or if you know that, for example, you're doing that olefin where you want to twist the pi bond and break it by twisting it, so you know the pi squared and the pi star squared configuration have to be equally mixed at the perpendicular geometry to give you the homolytic diradical cleavage of that bond, you can't use Møller-Plesset perturbation theory to do that. You shouldn't really. So what you can do is, in this kind of approach, MCSCF and CI both, right from the get-go, they say, okay, we admit that our starting wave function will itself have more than one determinant in it. So you'll start out with the wave function that's a linear combination of coefficients times Slater determinants. And what you're going to do is you're going to choose certain Slater determinants. So in that singlet S carbon, you would choose those three particular determinants that I don't want to write down again, but you can look back on earlier sessions. And those three determinants needed to be combined to give a singlet S wave function. So those determinants would be included in this list of determinants that you define in your space of determinants that are going to be included. And you then do the following. You say, I want to simultaneously minimize the energy. That is, you're going to have an expression in your derivation that's psi star h psi divided by psi star psi. You're going to take that energy expression and you're going to differentiate it with respect to these coefficients here, these C coefficients, to get one set of equations that I've written here, this summation over J of Hij Cj equals E Ci. That's going to be your equation that you get out of minimizing the energy with respect to these so-called configuration interaction or configuration amplitude coefficients. But you're also going to have in your working set of equations that arise by taking the energy expression, psi star h psi over psi star psi, and differentiating that expression with respect to the MO coefficients, these C nu I. Remember that each MO phi I is a summation over nu of C nu I times chi nu. Chi nu's are the basis functions. So you're going to get some equations also that I've not written down here. They are like the Hartree-Fock equations. So they involve some kind of Fock operator acting on these C coefficients equals an orbital energy times the C coefficients with an overlap matrix. The only difference is the expression for this Fock operator that comes in there is more complicated because it isn't just one single determinant anymore in the wave function. It's several determinants. But they're Hartree-Fock-like equations, I call them that. So the bottom line is what you're doing is you're taking an expression for the energy and you're simultaneously varying the configuration coefficients and the orbital LCAO-MO coefficients, both to minimize the energy. Now you say, what's different compared to just doing Hartree-Fock? Well, in Hartree-Fock, you only had one determinant, and you varied the LCAO-MO coefficients. Here you're saying that you might have 3 or 10 or 20 or whatever number of determinants that you want, some of which involve occupying different orbitals. You know, for example, in the pi squared and pi star squared, one determinant involves pi squared, another determinant involves pi star squared. So in the wave function, there will be pi and pi star will both be occupied to some extent in those terms in the wave function. So the MO coefficients of the pi and the pi star orbitals will both be varied to minimize the energy. In Hartree-Fock theory, if you chose, for example, pi star squared as your reference determinant, the pi squared, the pi star orbitals don't even enter into the Hartree-Fock energy because they're not occupied. So this is different. So what you end up with then is you end up with this so-called matrix eigenvalue equation, HC equals EC, that you solve for the CI coefficients. You end up with a set of Hartree-Fock-like equations that you solve for the MO, the LCAO-MO coefficients. Now, how do you do this? Well, these HC equals ECs, what are these H matrix elements? They're nothing but Hamiltonian matrix elements between or among the various Slater determinants. So the ith Slater determinant and the jth Slater determinant have various spin orbitals occupied. You have to use the Slater-Condon rules to construct these matrix elements between the ith and jth Slater determinants. You do that, you form this Hamiltonian matrix H. You get, now from the Hamiltonian matrix, you get, of course, a lowest energy eigenvalue, a next one up, a next one up, a next one up. You have to make sure that you choose the CI coefficients for the energy eigenvalue that you're interested in, ground state, excited state, whatever. Okay, so that's what you do basically in CI. So in the MCSCF. So I just want to make some comments now about what goes in here. Number one is in perturbation theory, if you reflect back on it, you had a reference determinant that said, this is the Slater determinant I want to use to start my whole calculation. That's where you, the scientist, got to decide how the orbitals were occupied in the determinant you were interested in. That defines psi 0. From that stage on, the procedure of Møller-Plesset determined what other determinants came in with what weights or what amplitudes. You never made any choices except what is my reference determinant I'm going to start with. Am I interested in the ground state of water, or am I interested in some n to pi star excited, or n to sigma star excited state of water? That's where you determined through psi 0 where your state of interest was. Here, though, in MCSCF theory, you have to determine a space of determinants. That is a set of them, for example, pi squared and pi star squared, or for the singlet S of carbon, those 3 determinants. They might be the ones you include. So you have to make a choice of what is your set of what we call reference determinants, the determinants that are included in this starting point. So in MCSCF theory, what you do is you make that choice, singlet S carbon, pi squared and pi star squared for the olefin. Then you could do a MCSCF calculation where you only use those sort of chemically intuitively chosen determinants, and you could do an MCSCF theory at that level. That would be like a minimal valence space MCSCF theory. Nothing wrong with that. Sometimes, though, what you do is you say, well, I want that space of determinants, but then what I want to do is to also add in determinants that are maybe doubly excited relative to that set. So you might have 3 determinants in your reference space. You might take the first determinant and do all possible double excitations, take the second determinant, all possible double excitations, third determinant, all possible double excitations, and include these doubly excited determinants in your space. If you, for example, wanted to put in dynamical correlation where the electrons can dance against one another. Probably you would choose doubly excited determinants first, because we know they're more important than singly excited determinants, Briron theorem. Now, you could be stubborn and say, okay, I want to go beyond that. I want to take my reference space of determinants, double excitations. I want to include some single, some triple, some quadruple. Go ahead. Put more and more and more in to get a bigger and bigger description of your wave function. The problem is things get out of control very quickly if you go wild this way. For example, if you have, say, m orbitals, let's just keep in mind this water molecule. Say we had water molecule where there's 5 occupied orbitals in the ground state, and suppose that maybe we only had a basis with 5 more virtual orbitals, so a total of 10. So there might be 10 orbitals, and suppose we had 10 electrons. Well, if we look at how many single excitations there would be, then there's going to be 5 orbitals out of which we can pull the electron, and 5 orbitals into which we can put the electron, so that would be 5 times 10 minus 5. The number of doubly excited determinants would be like the square of that, roughly, and so forth. Let me just give an illustration of how bad this can be. Suppose that you had this situation where you had 10 electrons in 10 orbitals. This was, see, this 2K here would be 10. This just means how many electrons there are. So suppose you had water molecule and you wanted to take the 10 electrons and you said, I'm going to be very stubborn. I'm going to put the 10 electrons in these 10 orbitals in all possible ways. Well, if you do that, you would end up with 63,504 Slater determinants total. You say, okay, I can handle that. But then suppose tomorrow you said, I want to do a calculation now on the water dimer. So you bring 2 water molecules and you say, now I've got 20 electrons and I've got 20 orbitals, because I had 10 for each water, and I want to distribute these 20 electrons in the 20 orbitals in all possible ways. Now you have what? 34,134,779,000, etc. So because of this all possible ways of distributing electrons among orbitals, if you start to put in singles, doubles, triples, quadruples, all that stuff, you cannot do that. These are what are called full configuration interaction calculations, where you distribute the number of electrons you have fully among all the possible orbitals that you have. They can't be done except for few electrons, maybe 20 electrons in 20 orbitals. It can be done these days, but that's about as big a calculation as any human being can do. Why? Because if you have 34 billion Slater determinants in a calculation, you have a matrix of 34 billion by 34 billion, even though it's very sparse. You have a lot of elements in there, and you have to calculate at least the lowest energy eigenvalue of that matrix, and an eigenvalue calculation takes of the order of the dimension of that matrix squared to get one eigenvalue, or the dimension of the matrix cubed to get all of them. So you can't be doing something that's 34 billion squared. So basically you can't do these full CI type calculations. So the bottom line is, in most MCSCF calculations, what one does is to use chemical intuition to say, first of all, what are the important reference determinants that you must include in your calculation? Pi squared, pi star squared. Or if you're breaking a sigma bond, sigma squared, sigma star squared. At least that. Then usually what you do is double excitations out of those determinants. That's usually about where people do MCSCF theory. What they then do is they essentially vary the orbital energies and the CI coefficients. So they carry out a CI calculation forming this matrix that's Hij to get the lowest energy E. They use this so-called Fock-like matrix that I didn't show you the expression for to optimize the orbital MO coefficients of the orbitals that are occupied in any determinant that's appearing in the wave function. And they go through that procedure. That's MCSCF theory, how it's normally practiced. One of the things, though, that I'd like you to notice is that in MCSCF theory, and I'll go back here to this, the Slater-Condon rules that you use to evaluate these matrix elements in the Hij, those Slater-Condon rules will eventually have those matrix elements expressed in terms of 1 electron and 2 electron integrals involving these spin orbitals, these molecular orbitals that are in here. Also, in Møller-Plesset perturbation theory, if you remember back on that, the second order energy, for example, had in its numerator some Coulomb minus exchange integrals squared divided by orbital energy differences. Those Coulomb and exchange integrals involve molecular orbitals. So what I want to now discuss for a few minutes is, how do we get these integrals that arise in the configuration interaction Slater-Condon rules, these molecular orbital I, molecular orbital J, 1 over R, 1, 2, molecular orbital K, molecular orbital M, that also appear in the Møller-Plesset perturbation theory? How do we get these 2 electron integrals, as we say, in the MO basis, that is involving the molecular orbitals? Because in a computer program, the thing that can be evaluated in the computer program is these 2 electron integrals chi I, chi J, 1 over R, 1, 2, chi K, chi L. These atomic basis functions, these Gaussian functions, contracted or uncontracted, expressions are available for these two-electron integrals involving Gaussian functions. But that's not what appears in the Slater-Condon rules for MCSCF theory or in Møller-Plesset perturbation theory. Instead, it's these molecular orbital-based 1 over R12 integrals. How do we get those? Well, you say, oh, that's easy, because each of these phi's is in turn a linear combination of the chi's. So wherever you have phi I, phi j, phi k, phi l, all you do is, for example, for phi j, you plug in sum over mu, cj mu, chi mu, plug it in, and that's simple. Yeah, intellectually it's simple, but let's think about the dimension of this problem. The problem basically is that if you have, say, m basis functions, they're of the order of m to the fourth of these chi two-electron integrals. There's also of the order of m to the fourth of these phi things. So if you were stupid and went to your upstairs into your office and said, I'm going to write a computer program that goes more or less as follows. For each, so I have a do loop that says for I, for j, do I, do j, do k, do l. That would be the phi I, phi j, phi k, phi l. Then within that you say do mu, do nu, do kappa, do gamma, because you're expressing each of these phi's as a summation of c, j, mu, for example, chi mu. You would have an 8 nested do loop there. That would be m to the 8th operations. You can't do that. I mean, 100 basis functions to the 8th would be 10 to the 16th operations. So that's not how these integrals are evaluated. And there's a little trick here that I just want to show you, but the bottom line is that to evaluate these two-electron integrals in the MO basis, of which there are of the order of m to the fourth of them, requires you of the order of m to the 5th calculational operations to do it. The reason I raise this issue is that this is one of the more time-consuming, expensive steps that we've had. So far, all we had in Hartree-Fock theory was m to the fourth two-electron integrals. M cubed was the number of operations it took to take the Fock matrix of dimension m by m and find all of its orbital energies and MO coefficients. But this is the worst-case scenario so far, m to the 5th. So here's how basically a computer program does these so-called two-electron integral transformations. It first starts out with the two-electron integrals in the AO basis, this so-called chi that I've written in the first line of this expression. It takes, for example, the last chi sub L, multiplies through by CML. M is going to be an MO index, and L is this AO index that labels chi L, and it sums over L. So it takes this list that, so the do loop here would be basically do I, do J, do K, do L, and do M. And so what would happen is there'd be a sum over L basically. And the output would be something that has I, J, K, M as its indices. What's called an intermediate partially transformed array or integral list. There's m to the fourth of these, there were m to the fourth of those, but because we summed here, this step involved m to the 5th total operations to get all m to the 4th of those. Then that partially transformed list, if you want to get real picky here, you could erase now from your disk these original integrals chi, they're gone. You now have chi, m, phi m. So now we take the chi, phi list, multiply it by another c, and sum over this index k to get another array that's chi, phi. We can erase this list that's chi, phi. I know this sounds sort of crazy to go through this, but that's a second partial transformation. Then we do, and that takes another m to the 4th operation to do it. Then we take this chi, phi list, multiply by another c, and sum over the j to get chi, phi. Then finally, we take the chi, phi list, multiply by another c, and sum to get the phi. So this 4-index transformation is carried out in 4 sequential steps, each of which requires of the order of m to the 4th operations, m to the 5th operations. So this ends up meaning that this list of MO integrals requires of the order of 4 times m to the 5th operations to give this final integral list that is of the order of m to the 4th in size. Now, I dwelled on that because this is one of the most important and time-consuming operations in most ab initio calculation programs, and it's something that if you're doing MP2, MP3, MP4, CI, MCSCF, you have to be aware of it because the program is going to have some step in it that involves this integral transformation that's going to be m to the fifth. Now, I should be real precise. People have taken the second-order Møller-Plesset perturbation theory expression and recast it in a way that doesn't involve the integrals in the MO basis, and they've shown actually that you can express the second-order Møller-Plesset energy in terms of just the atomic basis function integrals without requiring the MO integrals. But generally, for higher-order Møller-Plesset, CI, MCSCF, and other techniques we'll talk about, this integral transformation step is necessary, and it's m to the fifth. It's the worst-case scenario. Okay, so what do you then do in the MCSCF theory? Well, like I said, you have to make a choice of configurations. In that choice of determinants that you have in your reference function, or maybe double excitations or singles, whatever, that whole collection of determinants is labeled I and J. You have to form an Hij matrix, a square Hamiltonian matrix, whose dimension is the number of these configurations, called NC here, or number of determinants. You have to find, if you're interested in just, say, the ground state of this problem, you would get one energy out. So to calculate one eigenvalue of this NC by NC determinant, or matrix, you would require of the order of NC squared operations. So if this were, say, a 10,000 by 10,000 matrix, you would require of the order of 10,000 squared, or what would that be, 10 to the 8th operations to do this, finding one orbital, or one energy, E, and one set of CI vector. The CI vector is these configuration expansion coefficients for these determinants in the wave function. You would also have to carry out a set of Hartree-Fock-like SCF equations for these LCAO-MO coefficients of the orbitals that are occupied in any of the determinants that appear in your wave function. And that requires of the order of m to the third operations, because this Fock matrix is m by m. Now, MCSCF has advantages. It can describe bond cleavage, because you, in your choice of reference determinants, can put pi squared and pi star squared. But you got to have the brains to put those into the wave function in the first place, and then it can describe bond cleavage properly. And it can give a proper spin eigenfunction, like for singlet S of this carbon atom. It can give that thing. It can also give a property that we call an energy that is size extensive. And what that means is that if you carry out a calculation, say, on water molecule using a certain basis set, and you say, I'm going to do water molecule, and I'm going to include the Hartree-Fock determinant, and say all double and single excitations. Okay, and you get an energy. And then you want to do a calculation on a water dimer, and you say, well, first of all, let's do the calculation when the two are far apart, and we'll bring them together, and we'll get a potential surface. Well, when they're far apart, you expect if you do a calculation, you ought to get twice the energy you got in the water monomer. If you don't, something's wrong. And this characteristic of getting the energy that's twice the energy for the monomer as when you do the dimer, if the two things are far apart, is called size extensivity. So MCSCF theory can give energies that are size extensive. Now the problem is, and also it can give what are called upper bounds. That is, it can give energies that you know that if you put in more and more and more configurations, the energy will go down and down and down, and it will never go below the true energy because it's a variational-based methodology. There are some problems, though, with MCSCF theory, and in my point of view, one of the biggest problems is that what you're doing here is you're trying to vary many parameters to get a minimum. That is, you have many, many, many of these LCAO-MO coefficients. Say you have 100 basis functions and you have maybe 12 orbitals that are occupied in some Slater determinant in your wave function. Then you would have 1,200 of these coefficients, these MO coefficients, and maybe you have 246 configurations or determinants in your wave function, so you'd have 246 of these CI coefficients. So what you're trying to do here is to find an energy minimum, a minimum of a function in a space of parameter that is this 1,200 plus this 240, so 1,440 dimensional space. And that's a very difficult thing because this space has many little undulations and maxima and minima on it. So it's a very difficult high-dimensional energy minimization process. But still, it certainly is an approach that one can use, and it should be used when one has situations where a single Slater determinant is not going to be useful. Now, there's another approach aside from MCSCF. In MCSCF, we varied the CI coefficients and the LCAO-MO coefficients both to try to optimize the energy. The hard part of that, as I tried to stress at the end of that last slide, was that it's a high-dimensional energy minimization process, largely because the number of parameters in the MO coefficients is very, very large. Another approach is called configuration interaction, and this is like simplification in a sense of MCSCF. What you do in CI generally is you say, I have one determinant, maybe even if it's not going to be, for example, it might be pi squared, and you might know that pi star squared is going to be important to include, but you're going to stay still. I first will say pi squared is my determinant. I'll do a Hartree-Fock calculation on that, but I won't use perturbation theory to try to estimate the coefficient of the pi star squared configuration. I will use a variational approach. So in configuration interaction theory, what you do is your LCAO-MO coefficients for all the spin orbitals, occupied and virtual, are first determined by doing an SCF calculation. Maybe what you do is a small MCSCF calculation, for example, pi squared and pi star squared only, two determinants, to get some orbitals, some MOs, and you freeze those MOs, so you don't mess with them anymore. And then what you do with that chosen set of MOs, maybe from Hartree-Fock or from a small MCSCF, they're no longer optimized, they're just optimized at an initial step. Then what you do is you say, now, I'm going to take a wave function that's a linear combination of determinants with frozen molecular orbitals I won't mess with anymore. I will minimize now psi star h psi over psi star psi with respect only now to the CI coefficients. And you'll get this secular equation, HC equals EC, of dimension, number of configurations that you've chosen. It might be your reference, guys, single, double, whatever you choose to do, you have to make that choice. So what you're doing now essentially is you're just mainly spending your computational time primarily on doing these large matrix eigenvalue thing, the so-called configuration interaction step. Now CI has advantages, again because it's variational based. The energies you get out are upper bounds because it's variational based. In other words, they can never go below the true energy. Also, just like in MCSCF theory, when you come to this secular problem, the HC equals EC, you can get the lowest state, you can get the next eigenvalue, you can get the next one. So you can get several eigenvalues, so you can get approximations to excited state energies, same as in MCSCF, you can do that there too. Some of the disadvantages, similar to MCSCF, you have to choose the important determinants. Like in Møller-Plesset theory, you only made the choice of the first determinant. But here you have to choose which determinants you want to include. Singlet S, carbon, 3 of them. Pi and pi star, pi star squared for breaking the bond. You've made that choice. You then choose, do you want to include single, double, or we really should say double excitations first, then single, triple. You choose all that stuff. The scaling of the computational effort grows rapidly as the number of excitations. We showed this example earlier. If you try to include high-level excitations of even 10 electrons in 10 orbitals, things just get out of hand. So the computational size of the secular problem will get very much out of hand unless you make wise choices of configurations to include. Also, there's this m to the 5th process in transforming the 2-electron integrals from the MAO to the MO basis that's necessary in CI and MCSCF theory, and generally in MP series too, for MP3 and higher. And there's the scaling of this, finding the eigenvalues of this matrix. It's going to be scaling as the square of the dimension of that matrix, so the square of the number of configurations you've chosen. So that's one of the disadvantages there. So this is the end of session 7.